Welcome back to my course on Fundamentals of Electrical Engineering. We were doing the fourth module in Signals and Systems, and therein we had reached the fifth session where we are looking for Fourier transforms. So Fourier transforms, we had also looked at the general structure. Let's suppose you remember that mostly we were looking at rectangular functions, either in the time domain or in the frequency domain, wherein the other component would be, or their counterparts would be sinc functions in general. So this is the most prevalent kind of questions that are coming in gate examinations, and in this session also you might be encountering the same. And another aspect that we touched upon was about so we had also looked at the even functions which have derivatives of odd nature, but their Fourier transforms happen to be real, whereas the odd functions will have imaginary components of frequency in their Fourier transform. So let's look at a similar problem here. This is the first problem in this session associated with Fourier transform. So we see that we have x1 omega. Of course, it's the Fourier transform of x1t. We can call it as x1t, wherein we see three triangular structures with amplitudes as shown, as also with the frequency with the frequency dependence. If you look at x2 omega, it is just a reversal or what is called as a folding of the amplitudes of the Fourier transform along the omega equal to 0 axis. Okay, it's identical to just a flat folding of it. Okay, and this happens whenever we are having the if x1t has a Fourier transform as shown, then x1, the complex conjugate of x1t will have what is called as x1 minus omega. Okay, so let's see what the problem asks of us. Suppose x1t and x2t have the Fourier transforms as shown below. Okay, which is obvious. Which one of the following statements is true? Okay, so x1t and x2t are complex, and x1t, x2t is also complex with non-zero imaginary part. This is not true, because if x1t and x2t are complex, then their product will be need not be complex if they are complex conjugates. In this case, it's very clear that the x1t has a complex conjugate, which means that they are complex in nature, but the product of complex conjugates will be real in nature. Okay, so we discard B option as well, but option C is speaking about the exact nature of what we saw so far. That is, x1t and x2t are complex. They are complex conjugates too, and so their product is going to be real. Okay, so that's all in the first problem, which is just an understanding of the fact that xt, if it has a complex conjugate, if it's complex and has a complex conjugate, then the Fourier transforms will be just folding of each other at omega equal to 0. So moving on to the second problem, consider signal defined by xt is equal to e raised to j10t for t less than 1. Okay. For the magnitude of t, so long as t is the absolute value of t is less than 1. Okay, everywhere else it's going to be 0. So it's just an exponential function, and it's very clear to see that it will be just a window. Okay, the functional appearance will be just like a window, but of course exponential nature. Okay, so let's take the Fourier transform, because its Fourier transform is asked. Okay, so x omega is equal to, the signal lasts only from -1 to +1. So though when you take the Fourier transform, you go from -infinity to +infinity. You go, in this case, because the signal lasts only between -1 to +1, you take the limits from -1 to +1, and then e raised to j10t, you multiply by e raised to -j omega t, okay, as usual, and then you take the integration with respect to time. Okay, so it's obviously when you put them together, it becomes e raised to -j omega -10 t. Okay, so when you take its integration, minus j omega minus 10 comes on the denominator, and it is as it is, and then you put the two limits of minus 1 and plus 1. Okay, so obviously you get what is called as a since there is also a j in the denominator, you are getting a sine function. Okay, and the sine function with the of such a nature, that is omega minus 10 is going to be the theta there. So sine omega minus 10, and since it has already come on the denominator, so we have omega minus 10 on the denominator as well. But the j was already taken along with the 2, so there's a 2 on the numerator. Okay, so 2 sine omega minus 10 by omega minus 10 is going to be the outcome of the integration of taking the Fourier transform, wherein the limits have been reduced to minus 1 to 1. Okay, so obviously answer A is going to be the option that we are going to select from amongst the 4 given. Okay, let's go to the third problem. It tells us that let ft be a continuous time signal and let f omega be its Fourier transform defined by f omega as usual. Okay, minus infinity to f plus infinity ft e raised to minus j omega t dt. Let's define gt by gt is equal to minus infinity to infinity fu e raised to minus j ut du. Okay, this is just this is similar to what we call as the taking the Fourier inverse, but of course there was a 1 by 2 pi there. Okay, what's the relationship between ft and gt? So what's the relationship? The relationship happens to be that they are going to be proportional to each other except for the factor 2 pi. Okay, but then this is not always true, because when you are taking the integral and using e raised to minus j there, then this is true only for the even functions of ft, or else for odd functions a j may appear and it may also disappear from amongst the two. Okay, so obviously answer B, option B, where gt would be proportional to ft if ft is an even function is true. Okay, so fourth problem, okay, so now we have again a rectangular function xt is equal to rectangular t minus half, where rectangular x is equal to 1. Okay, if you have rectangular x is equal to 1 for minus half to x to less than half. So this is the general way of expressing a rectangular function, minus half to plus half. So the width is only 1. Okay, okay, and then we are having rectangular t minus half. Okay, let's see, and 0 otherwise. Then if sinc x is equal to sine pi x by pi s. So this is the normalized version when we are having the pi as well. Okay, otherwise it's sine x by x. Okay, the Fourier transform of xt plus x minus t. So xt is rectangular t minus half, and x minus t is rectangular minus of okay, you can take out minus, so it again becomes it's the same as equal to minus of t plus half. Okay, so we have, okay, so now, so when you add them together, xt and x minus t together, it's okay, it's actually just shifting. When you're talking about t as x rectangular t minus half, it means that you are having a rectangular function which has been shifted by t equal to half towards the right. Okay, so that's the orange version. And when you are going to reverse it as is given by x minus t, then you have the blue version. So it fills up the entire amplitude of magnitude equal to 1 from minus 1 to plus 1 now, rather than from minus half to plus half. Okay, so what do we have here? So if you are taking the Fourier transform, it's the same as equal to 2 sinc omega, where omega will now replace x in this the defined nature of sinc function as sine pi omega by pi omega. Okay, so this is what we have here. So and so let's look at the answer. The Fourier transform xt plus x minus t would be, okay, of course we are going to get 2 sinc omega or sine pi omega by you're going to get sine pi omega by pi omega. Okay, so let's look at sinc omega by 2 pi. That's not true. We need to have a 2 there, and omega is not, it's not like that. Okay, similarly 2 sinc omega by 2 pi is also not true. But on the other hand, if you look at 2 sinc omega by 2 pi, so omega 2 sinc omega 2 pi has been defined as equal to sin omega 2 by omega by 2, because you have to since sinc x is defined as sinc pi x by pi x, so sin omega by 2 pi will be defined as equal to, so you have to multiply it by pi and pi on the numerator and the denominator, so you will have sin omega by 2 by omega by 2. Okay, I suppose this is clear. Okay, so now let us replace 2 sinc omega by 2 pi as sin omega by 2 by sin omega by 2, and so when you multiply it by cos omega by 2, you have sin omega. Okay, sin omega, you have sin omega, and you also have an omega square on the denominator. You have some omega on the denominator, and 2 goes up. Okay, so it's obviously the same as equal to sin omega. So it's the same as equal to 2 sinc omega. Okay, so that's why we go for option C. Okay, so just a manipulation. It's all given in the slide. So let me hope that you'll be able to understand it even better once you look at the contents in the slide as well. Okay, so moving on to the 5th problem. There's a little bit of manipulation in all these problems. Let me hope that you'll be able to absorb them very quickly and do such problems very easily. Okay, moving on to the 5th problem, a signal xt, sinc alpha t. Again, it's a sinc function where alpha is a real constant and sinc x is given by sin pi x by pi x in the normalized version. So here's the input to a linear time invariant system. Okay, so when you give it to a linear time invariant system, obviously you don't have any frequency, no harmonics. Okay, whose impulse response ht is equal, it's another sinc function where beta is a real constant. If min alpha beta denotes the minimum of alpha and beta, and similarly max alpha beta denotes the maximum of alpha and beta, and k is a constant, which one of the following statements is true about the output of the system? Okay, so we'll have so if the Fourier transform for normalized sinc function is the rectangular function, rectangle equal to 1 from minus half to half. Okay, just as we saw earlier. Okay, so that's why these two problems have been put in the same slide. Okay, so multiplying the Fourier transforms gives a rectangular function of smaller width. Okay? So smaller width in the frequency domain. So it's clearly the minimum of alpha and beta. Okay, just like convolution. Okay. 6th problem. If the Fourier transform of signal ht is h omega 2 cos omega sin 2 omega by 2, the value of h0. Okay, again we are encountering a rectangular function there, and so its value in time domain at t equals 0. When you write it with a smaller alphabet, it is referring to the time domain function. Okay, so if Fourier transform is of this nature, then the rectangular function is going to be its counterpart in the time domain. So h0 is going to be equal to 1. Okay, very simple. Okay, 7th one, xt is a positive rectangular pulse from t equal to -1 to +1. Okay, with unit height as shown in the figure. The value of x omega square d omega, where x omega is the Fourier transform of xt. Okay, so we have given the function in the time domain, and so you can use Pascal's relation here, because the integration from minus infinity to plus infinity of x omega squared, the magnitude d omega, is referring to the power of it. Okay, so now that can be equated to xt square dt. Okay, and in the time domain, the Pascal relation is minus infinity to plus infinity xt square dt. Okay, so once this is done, so we see that, so we can take xt square. What's xt square? It's going to be the square of this of the numerical value 1 from -1 to +1. So you have to take the area. That's obvious. Okay, so and then you have to take the area. So we have 1. Okay, going from the width of the rectangle is going to be 2, so 2. Okay, so that you multiply it by 2 pi to get the integration from minus infinity to plus infinity x omega square d omega. So we have obviously 2 into 2 pi, that gives us an answer equal to 4 pi, which happens to be option D. Okay, so in this session this is the only problem which was different. Mostly we were again focusing on the rectangular to sinc function and sinc function back to rectangular, and some manipulations at most in most cases, and the obvious the obvious solution that I've tried to convey here is that you don't need to do the problem in totality. You just need to observe and pick out the relations. Like for instance, when we had sinc omega by 2 pi, we used the normalized sinc function. Sinc x is equal to sine pi x by pi x. So we saw that it was the same as equal to sine omega 2 by omega 2. And when you see sine omega 2 and cos omega 2 with a 2 or without a 2, you can obviously get what is called as sine omega. Okay, and then you have omega on the numerator and denominator, sine omega on the numerator and sine omega on the denominator, you will have what is called as the sinc function coming out. Okay, so all those things are with of course pi in this case because they were normalized. Okay, and we also saw we also took a Fourier transform wherein we saw that when we are having an exponential pulse e raised to j 10t between -1 to +1, we have what is called as we again get the same old. So it's just like a rectangular function, though it's exponential in nature. We still get the sinc function. Okay, in the Fourier domain. Okay, so and we also repeated the concept that for real for even functions, the Fourier transforms happen to be real, and their derivatives will be odd in nature with imaginary coefficients. Okay, we also saw that when we are having the Fourier transforms of complex conjugates will be folded in nature along omega equal to 0 axis. Okay, or reversed. Okay, so in the sense, I suppose I have covered most of the problems that are generally appearing in the GATE examinations in this genre. Thank you.